Today, I'm going to talk about speed development and the role of advanced technologies, and especially the motorized resistance and assistance. I've started using the T-Apex technologies since 2 years now. So today we're going to explore how motorized resistance technology and specifically the function of the T-Apex technology allow us to design sprint training with a level of precision that wasn't possible with traditional assistance and resistance training tools as it relates to speed. So we look at how the system let us manipulate force and velocity across different phases of the sprint, and how the advanced settings in the normal and overspeed mode can be used to target specific neuromuscular adaptations. We're talking about speed, which is one of my favorite topics. Today, early morning, the very first session of today's summit, my friend and colleague Gareth Walton from Access has started talking about speed, and especially multi-directional speed. So the first question to answer when it comes to motorized resistance training is why we're using motorized resistance training. We know that traditional resisted sprint training, such as sled, bands, towing systems, they often apply a single fixed stimulus, so one load, one speed, and one stimulus across the whole sprinting movement. So one load, one speed, and one constraint. Okay, not because coaches don't understand sprint phases, but because the tools themselves cannot adapt dynamically during the different phases of the sprint. And we know that sprinting is a rapidly evolving task, and force orientation, contact times, the different coordination demands change step by step, and motorized resistance allows to shape force and velocity across the sprint, match the resistance to sprint phases, and improve both the specificity and transfer. So the motorized resistance training is going to solve the limitation of traditional tools by allowing us to shape that stimulus in real time. So it's going to match the mechanical and neuromuscular demands of each phases of the whole sprint. Let's understand what is motorized resistance training. We know that motorized resistance training uses a control motor to apply resistance or assistance that can change instantly based on velocity or based on distance. Okay, and this can give us three main advantages. So we're going to have more precision because we can prescribe the exact loads that we want to in a specific phase of the sprint, the exact loads that we want at the start in the acceleration phase, the loads that we want to apply during the transition and during the maximum velocity phase. The responsiveness, because the systems adapt to the athlete's movement in real time, and the repeatability, because every rep is consistent, and which is essential for both monitoring and for a proper progression in training. So this allows sprint training to become phase specific, to become repeatable and precisely controlled. Why the T-Apex technology is different? The T-Apex is not just a resisted sprinting or towing device. and stands out because it treats the sprint as a sequence of phases, okay, rather than a single event. So instead of applying one uniform load or one uniform towing speed, it allows us to change resistance or velocity mid-sprint. Okay, so this means we can overload acceleration, okay, without compromising the upright mechanics of the maximum velocity phase. Okay, or we can expose athletes, let's say, to overspeed only when they are mechanically ready. Okay, that's the first system that truly respects the biomechanics of sprinting. So we have the dynamic resistance changes. We have a velocity-based triggers. So we can input that the system is going to change the load once an athlete reach a specific velocity threshold. So we have a distance-based segmentation. So we can segment the different parameters based on the distance. So we want for the first 10 meters, for the second, and so on. And the overspeed can be easily and precisely controlled for the curves. Sprinting is not one movement, but it's a progression. I like to say it's a progression of mechanical problems. So each sprint includes early acceleration, which is force dominant, so longer contacts, horizontal force application, projection. Mid acceleration is a sort of transition. Okay, it's a transitional, and there is a rising posture. Posture is rising. There is an increase in stiffness, and a shorter contact time. Then the upright and maximum velocity is coordination dominant. So there are extremely short contacts that has more an elastic behavior and precise timing of each muscle and movement. So each phase requires a different stimulus, different force, and different constraints. So if we apply the same load or speed across all phases, we inevitably compromise part of the sprint. In the T-apex, we have different modes of training. So there is the normal, the isotonic, and the overspeed. For our purposes, we will have a look now at the normal mode and overspeed mode and their advanced settings. The normal mode is for the linear training, for the linear sprinting training, okay, where we can apply resistance to the linear sprint, okay? The overspeed mode is to apply assistance. So we will look at the differences between both. So the normal mode is designed to improve acceleration performance by increasing horizontal force production and reinforcing the mechanics, the projection mechanics. So projecting the center of mass forward. Okay, so the goal is not simply to make the athlete work harder, but to create a constraint that enhances the qualities that matter the most in the first 30 meters. So pushing, projecting, and orienting forces backwards. That's where we need to apply forces during the acceleration phase. So the primary goal of resistant sprinting, okay, with the normal mode, with the motorized resistance provided by the T-apex, is to improve acceleration performance by increasing the horizontal force production and projection quality. So the resistant sprinting targets mainly the push mechanics, the first step explosiveness, and early acceleration efficiency. But when it comes to, let's get back to constant resistance, that it's the one we have with traditional sled, towing bands, parachutes. Why constant resistance has limitation? A single resistance value is a compromise. So it's heavy enough to meaningfully overload the first steps, but light enough not to distort the mechanics later. So the main problem here is that acceleration benefits from load, but upright sprinting is extremely load sensitive. So if resistance stays high too long, so the risk is that athletes overlean. Okay, the athletes overlean. It's over pushing. It may delay upright posture and lose the rhythm, which is essential in the maximum velocity phase. So constant resistance forces us as a coaches to choose between early phase benefit and late phase quality. Okay, so we know that acceleration, as I told you, is highly load tolerant and often benefits from resistance, while upright sprinting has a very narrow tolerance for load. Okay, and in most cases benefits more from velocity exposure than from resistance exposure. What does it mean? Mean that acceleration benefits almost always from load for mechanical reason, because ground contact times are longer, force is applied more horizontally, and the athlete is still producing velocity, not maintaining it. Adding resistance in this phase increases time under tension, encourage backward force application, reinforces projection mechanics, and matches the force dominant nature of the acceleration task. This is why resisted sprinting works so well early. But upright sprinting is different. Upright sprinting, max velocity, is not a force production problem. It's a force application and coordination problem. So the key characteristics there are extremely short ground contacts, high vertical stiffness, precise timing, minimal braking, high elastic contribution, and very narrow technical margins. So any external load in this phase may lengthen contact time, alter stiffness, may disrupt rhythm, changes the timing of the limbs, and increasing the risk of breaking forces. Okay, this is why most loading strategies can be detrimental once the athlete has reached the upright position. Okay, but the question is load always detrimental to upright sprinting? So we need to ask this question, but the answer is that only under very specific conditions, and there are three main exceptions from our experience, and they are narrow. The first exception is that very light and velocity preserving load, because if the load is extremely small and does not reduce velocity and does not alter contact time and does not change posture or rhythm, then it may be occasionally used for technical awareness. Okay. The second exception is elite athletes with very high level of stiffness and control. Okay, because highly trained sprinters, they have very high vertical stiffness. They can tolerate small perturbations, and they can maintain mechanics under slight load. In these cases, microloading may be used briefly and often for rhythm or posture awareness, and usually over very short distances. And the third exceptions from our experience is that if the load is used as a diagnostic or teaching constraint, sometimes load is used to expose some technical weaknesses, to highlight some breaking or posture issues, and to create a contrast, okay, not adaptation. In this case, the load is not meant to improve upright sprinting, but it's meant to reveal technical problems, technical issues. So in this case, it's not a coaching tool, but this is going to not be a performance tool, but it's going to be a coaching tool, okay? So in the normal mode with the T-Apex, we have advanced settings. The advanced settings allow us to set different resistance values for different phases of the sprint, okay? So we can trigger the resistance change based on either distance or velocity. I mean, we can, if we input a certain distance threshold, it means that once the athlete has reached that distance, then the resistance can drop based on our input of 2 kilos, of 3 kilos drop, okay? Or we can set a velocity threshold. Once the athlete is reaching that meter per second value as a threshold, the resistance is going to drop by 4 kilos, by 5 kilos force, okay? So this means we can overload the phase that benefits the most from load, let's say early acceleration, and then automatically reduce resistance to allow natural mechanics in the transition and upright phases. So we can perform a full sprint training, okay, by adding the resistance input for each phases, okay? So this is going to create a phase specific loading. How that phase-based resistance works. So a typical setup might use high resistance, let's say for the first 8-12 meters to reinforce projection and backward force application. Once the athlete reaches a specific velocity or distance, the system drops to a lower resistance based on our input. So this is going to preserve the benefits of resisted acceleration while allowing the athlete to transition into upright mechanics without distortion. And it's a way to load the right qualities at the right time. That's extremely important. What are the coaching benefits of phase-based resistance? So this approach, the phase-based approach, gives us the best of both worlds. So meaningful overload early and clean mechanics later, okay? So it improves technical transfer to the unresisted sprinting, okay? Reduce the risk of over-leaning of the athlete in the upright sprinting phase or over-pushing, and allows us to individualize resistance based on the athlete's profile. It also creates more consistent outputs because the athlete isn't fighting excessive load in the later steps. So we're using one fixed resistance, load the phase that benefits from load, maintain sprint rhythm and posture, and improve transfer to unresisted sprinting, okay? Sorry, that's using a phase-based resistance, so setting different values of resistance for different phases of the sprint. So the result is going to be better acceleration without technical compromise. So phase-based resistance is ideal for athletes who need better projection, stronger first steps, or improved acceleration posture. Okay, it's also extremely useful in team sports, where the first 15 meters are the most decisive, because that advanced settings allow to emphasize the first 15 meters force production. So we can tailor the resistance change to the athlete's acceleration curve, ensuring that the stimulus is matching the actual mechanics rather than based on an arbitrary distance. Okay, and we can progress the athletes safely and individualize resistance without changing drills. The second modality that we want to focus on is the overspeed mode. Overspeed mode is going to target max velocity development. And unlike acceleration, max velocity is not limited by force production, okay? Max velocity, it's limited by coordination, timing, and the ability to maintain stiffness and relaxation at very high speed. Relaxation is an important element. And it's very, very important that you understand that when we talk about relaxation, we're not talking about the athlete being passive, but about the athlete relieving unnecessary tension in order to express maximum speed. And overspeed gives the nervous system exposure to slightly higher velocities than the athlete can produce alone. This is overspeed, which accelerates neuromuscular adaptation. Okay, so the primary goal of overspeed is to expose the athlete to slightly higher velocities, to improve coordination, to improve rhythm, to improve timing and relaxation at top speed. And it's also important to note that overspeed is not a strength tool, but is we can define it as a neuromuscular tool. And exposure to overspeed needs to be planned carefully, as it's very, very taxing for the central nervous system. So why overspeed must benefit from control and must be controlled? Overspeed is powerful, okay, but it's unforgiving. So if assistance is too aggressive or it's applied too early, athletes lose posture, overstrides, break, or tense up. So this not only reduces transfer, but increases injury risk. The key is control, progressive exposure. Assistance also must be introduced only when the athlete is mechanically, from a technical point of view, is mechanically stable and able to maintain technical integrity. So the key requirements of overspeed is that it must be progressive, smooth, and phase appropriate. The advanced settings in the T-Apex overspeed mode allow us to create up to 10 segments, 10 distance-based velocity segments. And this means that we can design a custom overspeed curve that ramps assistance gradually and peaks only when the athlete is upright and tapers if needed. So instead of one fixed tau speed, we can shape the entire velocity profile of the sprint. And this enables very precise control of the assistance. What distance-based segmentation allows, with the segmentation, we can keep assistance minimal during the first steps, increase it gradually during the transition, and we can apply peak assistance only in the max velocity window. Okay, so we can also stabilize the velocity plateau or taper assistance to maintain the required rhythm and dynamic coordination in the upright sprinting phase. So this makes overspeed safer, more specific, and more transferable. What are the coaching benefits of segmented overspeed? Segmented overspeed improve step frequency, the front side mechanics, and relaxation at high speed. So it's going to reduce the technical breakdown by avoiding any abrupt changes in velocity. It also allows to individualize the exposure to overspeed based on athlete stiffness, athlete's coordination, and athlete's level of experience. So the result is a more effective and safer overspeed stimulus, and the athlete stay in control of the movement. Practical overspeed application. Using overspeed is ideal for breaking maximum velocity plateaus. Okay, that's one of the most important reason why we can apply overspeed. It's to refine upright mechanics to prepare athletes for competition. It's especially valuable for athletes who struggle with rhythm, timing, or relaxation at high speed. So by controlling the overspeed curve, we can expose them to higher velocities without overwhelming their mechanics. That's extremely important in sprint training. So what are the key takeaways of this presentation? So the key message is that sprinting is phase specific, and our training tools should reflect that. With motorized resistance, it allows us to use a phase specific sprint training. Okay, so that normal mode advanced settings in the T-Apex allow us to overload acceleration without compromising technique. And overspeed advanced settings allow us to improve coordination at high speed safely and precisely. So with the T-Apex, it gives us the ability to design a full sprint training with both intention, with both specificity, and with more control. So the sprint training is becoming more planned and designed, and not improvised with not improper planning and loading. So hope you enjoyed the presentation about the T-Apex technology.